Picture this, you have a program. It works maybe not beautifully, maybe not elegant, but it works. For example, it processes a file, or it scrapes the websites, or it transforms the images, or it's doing some process while your laptop slowly takes off like a plane at night. But still there's a problem. It's slow. You open Task Manager or HTOP or Activity Monitor based on whatever OS system that you use, and you see that your CPU has 8 cores, maybe 32, and your program is barely using one of them. So at first you would think, easy, I will just add more threads, which sounds completely a good solution. More workers should mean more speed, right? But then you run the program again, and somehow it gets slower. Not slightly slower, much slower than before. And CPU usage is surprisingly high. The fans spin faster, everything looks busy, but the program takes longer to finish. So what happened? Did threads backfire? Well, not exactly. They just did exactly what you asked them to do. And that's a problem. Today we are going to talk about why more threads can actually make your code slower, why locks quietly destroy your performance, and why processes sometimes outperform threads, and why context switching is basically an invisible tax your CPU colleagues whenever you try to be clever. Because if you deep dive into all of this, there's a huge misconception there. Parallel code is automatically faster. This misconception is not true. Parallel code is only faster when the work can actually happen simultaneously. The overhead is small enough and the workers are not constantly fighting each other. And that last part matters more than people think, because threads are not magic. A thread is just another execution path inside the same process. And threads inside the same process share memory. They have the same heap, they have the same globals, same address space, and that's powerful because sharing data becomes easy. But it is also dangerous for exactly the same reason. If two threads only read the same variable, that's fine. But the moment two threads start writing to the same variable at the same time, things get ugly very quickly. Now you need the synchronization. You need locks, mutexes, atomic operations, this kind of things. Because without synchronization, your program can become non-deterministic, which is the professional way of saying it worked yesterday, it fails in production. Nobody knows why. Let's start with this. We have a shared counter in C++, like this in the screen. You launch 8 threads, you expect 8 million as a result of the counter. But you might not get 8 million because counter plus plus looks like one operation, but it actually isn't. Under the hood, it's more like read the value, add 1, write back the value. And in that case, if two threads do that at the same time, one update can override the other. There's no crash here, no warning, just wrong answers. Which is honestly one of the worst kind of bugs, because the program still looks correct. So you fix it with a mutex, like this in the screen. Now the answer is correct, but the performance, you may ask, possibly terrible, because every thread is fighting over the same lock. You created 8 workers, then built a doorway that only allows 1 worker at a time. The other 7 just stand there waiting, and waiting has a cost. The cost is like this. Your thread is waking up, it tries the lock, it fails, go back to sleep, and it gets scheduled again. And try the same process to get that lock. That overhead accumulates fast, and this leads to one of the most important lessons in multi-threaded programming. Threads do not make bottlenecks disappear, they expose them. Sometimes they amplify them. Now let's talk about Python, because Python adds another twist in this story. In a standard C Python, there's something called the GIL, or Global Interpreter Lock. Let's call it GIL. The GIL allows only one thread to execute Python bytecode at a time when it's running inside the process. This sentence just changes the concept, because if your Python code is CPU bound, your threads often are not really running in parallel across multiple cores. They are mostly taking turns. So the code like this may disappoint you, because in real world it's not really parallel code. So why does Python even have threads? Because threads are incredibly useful for IO bound work, waiting for web requests, waiting for disks, waiting for database, this kind of tasks. That thread is mostly idle, which means another thread can run while it waits. For IO heavy workloads, threading can improve throughput dramatically, but for CPU heavy Python code, threads often disappoint you. Sometimes they even slow things down, because now you are dealing with GIL overhead, scheduling overhead, and synchronization overhead. Even you need to consider cache disruption. At that point, the CPU spends less time doing useful work and more time coordinating chaos. So why do processes help? Because each process has its own memory space, its own interpreter, its own GIL, which means multiple processes can actually execute Python code simultaneously across across multiple cores. But there's a trade-off, and there's always a trade-off. Processes isolate memory, which is safer, but sharing data becomes much more expensive. If process A needs to send a joint object to process B, the data usually needs to be serialized, copied, and transferred, and at the end it needs to be reconstructed. That can become expensive very quickly. So threads and processes solve different problems. Threads make communication cheap because everything shares memory by default. Processes give you a stronger isolation and true CPU parallelism, but communication becomes more expensive. You need to pick your own pain. Until the next video, good morning, good afternoon, and good evening. Bye.